So in this section, we will implement Simpson's method of integration. We are going to integrate a function which is the x cube. So let's start by defining the function. So there's a function called fx, and I'm going to be passing on the value of x in this, and it is going to return x cube. So this is what is my function. And let's define the integration interval. So we are going to integrate this particular function from -1 to +1. So let the first limit be a and the second is b. And now we have to define the number of subintervals that we want for the Simpson's method. So if you remember, a subinterval in Simpson's method was -h to 0, or it could be 0 to +h. This whole thing put together, when combined together, becomes a complete interval, which is from -h to +h. So we have to figure out how many subintervals that we want so that we can calculate the value of h. So how we are going to do it is that we're going to ask the user to input this, and it has to be an integer. So I will convert it into integer, and it has to be an even integer because we are talking about 3 points per interval. So let's say enter the number of subintervals. So that's it. And once we get this data from the user, we are going to print it. And if you remember that the intervals are exactly half of the subintervals. Two subintervals put together make one interval. So we are going to then print the number of intervals. And in case if somebody has entered an odd number in the input, then we will just take the even part of it. So let's just run this code and see if it's working. So it's asking for number of intervals. Let's say I say 10 subintervals. So number of subintervals 10 and number of intervals 5. So let's see what happens if we enter odd. So here we are, 11 subintervals, and then it has got converted into even number, which is 5 intervals. Now we will calculate h. H is nothing but the entire integration interval, that is from b to a, divided by total number of subintervals that the user has inputted. So let's just have a look at this number also. So let's say there are 10 subintervals. That will result in 5 intervals, and each h will then be of 0.2 width. That's what it means. So moving further, before we move further, let's just plot this function and see whether it is working fine or not. So what we're going to do is define x values for this function, which is, I'll use a function called linspace, and I will take it from a to b in, say, let's 100 steps. And I will plot the y values of it by passing on these x values, and have a look at this function. So I can just have a rough plot of this x versus fx, and let me just activate some general settings here. So let me just disable this. Okay, when we run this, I say 10 subintervals, which result in 5 intervals. This is the x cube function, and we are required, and it's going from -1 to +1, and we are required to calculate the area under this curve through Simpson's method. So far the code is working. Let's move further. So I'm going to now disable this piece of code. So now we have to decide the x values of all the subintervals, and how we can do it is we can use the same trick. We're going to generate an array of linearly spaced numbers, and they will start from a to b. And how many number of such subintervals are there? There are n, so we're going to generate n such numbers, and because Python index starts from 0, so we have to increment this by 1. Let's just have a look at this array, what it means. So here we are. So I wanted 10 subintervals, so these are 10 numbers starting from -1 to +1, each separated by an h of 0.2. And now I have to generate a corresponding y value for all these subintervals. So that's easy. I will generate a function called fxi, and I will pass on all these values there. And let me just print all of them then. So again, 10 subintervals resulting in 5 intervals. I have x values here, and now I have 10 y values here. If you see, these are all cubes of x values. So a cube of -1 is minus 1, and the cube of 1 is 1. So we are getting these values. Let's move forward. So now we need a variable in which we are going to store the total area under the curve. Let's call it total area, the variable, and let's initialize it to 0. And we'll update this variable in a for loop. Now let's go to implementing this Simpson's rule of integration. Before we do that, we have to understand one thing, that for one particular interval, we need 3 points, y1, y2, and y3. And for the next interval, it will be y3, y4, y5. So let's get our indexing scheme proper before we implement this. So let's say in this for loop, for I in range, how many number of intervals do I have? I have n number of subintervals. So what am I doing here? I am trying to get the index of my y array, that is fx array, correctly. So let me just do a quick check whether my indexing is right or not. So I'm going to do a printing 2i plus 1 and plus 2. So I just want to run this code and check whether I'm getting the right integration points or not. So there we are. As I discussed, in Simpson's method, we need at least 3 points for the calculation to be done, y0, y1, and y2. And then we slide over to the next subinterval, which is y2, y3, y4. And then we slide over to the next subinterval, 4, 5, 6, 6, 7, 8, 8, 9, 10. So by using this index, I think we are going to achieve this. So I'm going to comment this out. And also we are talking about intervals here, even number of intervals. So we are going to run it for number of intervals that we have. So there are 4 terms to this formula. Let's split them and implement them accordingly. So let's start with term 1, which is nothing but h divided by 3. Let's implement the second term, which is this y0 term. So here, if you remember, this fxi is nothing but y for us. So we are going to extract these values from this array. And how we are going to do it, we have just seen this indexing scheme here. So point 0, 1, 2, if you remember, we have to extract first 3 points, 0, 1, 2. So how we are going to do it is we are going to take this array, which is fxi, and then we are just going to say this. So I am able to extract the first number, and then I'm going to use term 3, which is this one. So essentially I have to multiply it by 4 and same y array, and now the next element of this y array. So I'll just copy this and add 1 to it, which is the next element in this array. And similarly, I'm just going to copy the code for the 4th term, which is y2, and I'm just going to add 2 to it. And lastly, we are going to say, we're going to implement this complete formula. So we are going to write it this way: term 1 multiplied by a combination or addition of term 2 plus term 3 plus term 4. And this is for one iteration. This area is going to get calculated, and we have to continue to accumulate this area under the curve. Basically, we are simulating multiple parabolas now. So for the first parabola, this area got calculated. So if you remember, we had initialized a variable called total area, where we are going to accumulate this. So one by one, all the parabolas and area under them will get calculated and get accumulated in this particular variable. So let's pause here and see if our code is working till this point. So I don't need my plots yet. So I'm going to stop here and okay. So I have got a total area under the curve, which is 0.2. And if you remember, x cube is an odd function, and the area under this function will always be 0. So we are reaching there. We are not, we are very close to 0, but we are still not there. There's an error of about 0.2 here. So the next is that let's plot these equations. So I have my x-axis, which I have, okay, so let me just rerun this and So from A to B, I'm generating x-axis here, 100 numbers, and then I'm going to pass it on to my function fx, which is this, and then I'm going to plot this as I did earlier, and I'm going to call it, for LaTeX code I need to insert these two dollar signs, and I'm going to call it f of x, which is equal to x cube. So this is what is the label, and let me just plot it in say blue color. Okay, and let me activate some general settings of this plot here and see if it's working. So again, I'm going to enter 10 subintervals, and yeah, so we are able to plot this function. What I want to see is how the area under this curve is getting calculated. So for that, I will use another plot called fill between. And remember what I'm doing. I have already calculated x values of all the subintervals, and I have calculated corresponding y values of all those subintervals that we were talking about. So I'm just going to plot them. What did I call it? Yeah, fxi. So these are the two variables, and I'm going to reduce their opaqueness. Let's just call it 3 so that we are able to see them. And let me just paint this area in green. Okay, so you will see what's happening here. So I'm going to enter 10 subintervals, and here we are. So you see this green area is the area under the curve, which is what is the our motive, and this green area has been calculated using the Simpson's formula here. So as I mentioned earlier, that it's an odd function, which means that the negative area is going to be equal to positive area. If you see that this area, this green area, is all positive here, it is above 0, and this area is all negative because it's below 0. When you add them up together, it will become 0. So this is what we are trying to implement here. And with 10 subintervals, we see that there are some errors. You can see some spillovers. Let me just clarify them. Let's go for even lesser number of subintervals. Let's say 3. So now you can see with such low number of subintervals or less number of parabolas, we are not able to approximate this x cube properly, and as a result, my integration, which should be 0, result should be 0. It's not 0 because we have far too less number of parabolas, and my h interval is very high. It's 0.66. So how I can reduce it is by increasing the number of subintervals. Let's say I have 24 subintervals, and there you are. Now we are moving closer towards 0, and those overshoots which were happening earlier have disappeared. Let me just disable these print statements so that, okay, what happens if we have 100? So you see we are moving closer and closer towards absolute 0. What about 1000? There we are. Now we are 0.00, and this is there's no spillover of this green area anywhere. It is hugging the curve nicely, and this is what is the beauty of Simpson's method. Please note that the h value, the subinterval width, has become very small. It is 0.002, and that's the reason why the accuracy of this method has increased drastically. So that's the long and short of this method. I hope you've been able to understand the inner workings of Simpson's rule of integration, which is just implementing this formula, and it's a much better algorithm in comparison to the trapezoidal method.